Hey guys, what's going on? So today we're going to be talking about conformal transformations. So initially, before this, we were talking about electromagnetism, making sense of electromagnetism in GR. Now we're going to shift gears a little bit. We're going to talk about conformal transformations. We're going to talk about what it means to be a conformal transformation in this video, and then later on, we're going to conformally transform the Riemann tensor. We're going to take a look at a new type of tensor called the Weyl tensor. We're going to look at the Lanczos tensor and all this very, very interesting stuff. And then after that, we're going to dive more into the physics of things. I really kind of just want to get all this heavy math sort of done so that we can rely on this heavy math to do physics later on. So without further ado, make sure to hit that like and subscribe button. If you like this content, make sure to go onto my Patreon page if you want to support the channel. And let's get right into this now. So we're talking about conformal transformations. Conformal transformations are super, super important in understanding more higher level GR. Okay, so we're moving away from electromagnetism. We're going to shift our attention to this conformal symmetry. And a conformal transformation, here I'll just read off right here, conformal transformation is nothing more than a scale transformation. A general local transformation is defined as a scaling that depends on the location of spacetime. Okay, so just as an example, we have our x-coordinates, right? So our coordinate system, mu runs from 0 to 3, where the 0th coordinate is time, 1, 2, and 3 are spatial coordinates. And x tilde mu is a new or newly transformed coordinate system, and it's a function of the old coordinate system, right? So this new coordinate system is a function of the old coordinate system. So depending on where you are in space-time, that's going to tell us how what the new coordinate system is. So then that depends on where you are. Okay, so effectively this is a field. It's a field of transformations. Okay, and we have this new coordinate system. It's a function of the old coordinate system. Now, what exactly is this function? Well, when we're talking about conformal transformations, it looks something like this. Okay, where we have the old coordinate system, okay, multiplied by some scale factor, okay. The scale factor, again, depends on where you are, and this is that scale multiplication I was just talking about. So let's pictorially understand this. Suppose we have, that's a little bit big of a, suppose we have a field, and here's our newly transformed field. Okay, our field and suppose we're at this point. Okay, to get from here to here is a scale transformation, omega. Okay, and omega is a number. Okay. So this is a transformation. This is our conformal transformation. Okay, and let's now take a look at what happens to the metric. So recall the metric tensor is an object in space-time that mimics the effect of the inner product. So the metric effectively takes two vectors and spits out a number. That's what the inner product does. In this sense, we're preserving angles, which is a unique feature of conformal symmetry. Okay, so here, same picture, we have our old coordinate system and our new coordinate system, and here's our coordinate systems, and we're looking at this point. All right. And what we are doing is we are looking at the tangent space, right? So the tangent space and the tangent space contains an inner product, and that inner product is mimicked by a metric tensor, which is located in another space at that point. We've talked about a lot of this already, but we have this metric tensor, G mu nu, okay? And we want to transform this metric. We want to understand what it looks like in this new coordinate system, right? So we have G prime mu nu, okay? And we want to know what the transformation is from here to here. And this is the transformation. The transformation is just this right here. So we go from the old coordinate system to the new coordinate system. The new coordinate system. And you might think, okay, how is this preserving angles? Well, if you recall, the metric tensor mimics the inner product. The inner product, if the inner product is 0, that means the angle between two vectors is 90 degrees. And as the angle approaches 0, then the inner product increases, right? You can sort of think of the inner product as something that measures how much two vectors agree with each other, okay? So, and again, when we're talking about the inner product is in a tangent space, and we have two coordinate systems. We have a coordinate system, and we have two vectors in that coordinate system, and then an angle, okay? Well, again, that angle is measured by the inner product. The inner product is a proxy for the measure of this angle, and the metric tensor is a proxy for measuring the inner product, okay? So in this sense, we can understand that the metric tensor really, at its core, at its geometric core, measures angles between vectors, okay? And we want to preserve this. So, and when we preserve it, we're calling this preservation. We want to preserve this under a transformation. We're calling this preservation a conformally symmetric transformation. Okay? Alright. So, this means that the basis of the metric tensor must transform in this way, right? So we start with dx nu. This is our two small displacement unit vectors, and we now want to divide this by our omega factor, okay? And when we do that, we're going to say that this is the definition of our newly transformed system, right? So on this side we have G, on the side we have G prime, okay? And we could see here, just really quick, that this here, I'll just bring it down here, G mu nu omega is equal to G prime mu nu. Okay, this is the newly transformed, and you might think, well, why is this in the bottom? Well, it can be on the bottom or it can be on the top. It's just a scaling factor of G mu nu. Okay. So we're going to define it in this way, which means that if we take mu to equal nu, or nu to equal mu, then we just have this relationship, right? So here, where all we're doing is we're saying mu is equal to nu, and we have this relationship, and then from here we get this, and we get this through, let's see, we want to replace, so we're getting this here through this guy up here, right? Because we have that dx mu, or the new and the old prime. So this is the old coordinates and the new coordinates. This is the old coordinates, so we're replacing the old coordinates with the new coordinates. Okay? So dx mu prime, that is going to be this right here, right? So the new coordinates is equal to x mu omega nu, x mu omega nu. Okay? And then we can divide both sides of the equation by dx mu, which is why we have this in the bottom. Okay? So all we're really doing is we're replacing this guy with this guy, then dividing both sides by this guy. Okay? And so what we get is this relationship here. This is quite interesting. It's so let's look at this a little bit more. The derivative of this expression is just this expression. And why? Well, because dx mu, this is the product rule, right? The product dx mu, so we're taking the derivative of this times this, and then the derivative of this times this. So the derivative of this guy times this is this term here. The derivative of this term here times this is this term right here, right? Because dx mu is just 1. Alright, so we're getting somewhere here. Now we're going to replace this guy with this. And so that means the following equation must be satisfied in order to yield an invariant line element, or to yield something that could be akin to what a conformal symmetry would look like. Alright? So this is our equation, right? So we just took this, we replaced it with these two guys, and we have this. Now this is a differential equation. This isn't a course on differential equations. What I'll do right now is I'll just tell you what the solutions for this are, and it's quite easy to sort of show yourself how you can do this, but there's going to be two trivial solutions. One is a positive one, the other is a negative one. You can see that here. If you plug in positive 1 for all of this here, so when we get, if we have positive 1, this becomes negative 1. The derivative of 1 with respect to x mu, well, that's just 0. And then this is 1, and you'll get 1 equal minus 1 equals 0, and that's 0. Same thing you can do for the negative trivial solution, right? And this one's not so trivial. Plus minus 1 plus a, where a is a parameter that we have to choose, divided by x mu squared. And so you can actually plug this into here, and you can actually you'll actually be able to see that this is that everything's kosher. So so I'm just going to say right here that these are our 4 solutions. And since the solution must be positive, and we're interested in non-trivial solutions, the local transformation is going to be this right here. Right? We don't have to restrict ourselves to positive solutions, but we want the transformation to be a positive solution, so we're just going to focus on one, okay? And that one is going to be this. So we're changing A to L, and right now L isn't going to have play a significantly huge factor in this video, just because we're introducing the mathematics behind the conformal transformations. In later videos, we'll take a look at what this L could do to our solutions and what it actually, and we're going to be able to theorize what it could represent physically. But for right now, let's just call it a parameter. So this is our solution, and this is our conformal transformation. So you can, and this is a local conformal transformation because it's a function of x mu. So what this is telling us is that, if you recall, this is our rule. okay, for a conformal transformation. So G mu nu times that squared, well, that's going to be 1 plus 1 over x mu, undo that, x mu squared G mu nu. Well, the square root squared, that's just going to be, we can actually just get rid of the square root, right? So we get square root, get rid of square root, and we have something that looks like this, and that's our conformal transformation for our metric. Okay? Alright, so we have a form now for conformal transformation and what a conformal transformation has to look like. We now have a formula, an explicit formula that tells us what omega should be. Okay? So a local conformal transformation is therefore, we can confirm this, right? Because we could say dx rho, dx mu, where the nu is on the top, same here. Well, that's equal to this, that's equal to this. We've shown that to be true now, which is this right here, okay? And we can see that this is true because when we plug these guys into our formula for our metric, right? Because our metric is this guy times these transformations, this which is the inverse of these two guys. So we calculated these two, right? So we calculated these two, which are here. They're right here. We can actually now multiply by both of these guys, and we can take mu and nu to be the same, and we get back our transformation property here. So this here, just down here, is confirmation that this transformation does indeed work. And so this part here is not as important. What we're really interested in is this right here. This is the form of our, this is the form that we are after for right now, because later we are going to put this in the context of a conformally transformed Riemann tensor, right? So what we've done is we've taken our space-time. So here's our space-time, and we've transformed it. We've transformed it at some point. We had our metric. We had our metric, prime metric, and let's move these down for a second. These two guys were related by omega, and omega took the form of the square root of 1 plus 1 L over x mu. Okay, our point is x mu. Our point is x mu, our new coordinates. But now we can say, well, from our metric, we get our Christoffel symbols, and from our Christoffel symbols, we get our Riemann curvature tensor. Our Riemann curvature tensor again being, I'll rewrite that just to show all of its components. A Riemann curvature tensor, mu, nu, alpha, beta. Here we're going to have a newly transformed gamma, also our Christoffel symbols. Here we're going to have our R, mu, nu, gamma, alpha, beta. This is prime, however, prime. And we, this is our conformally transformed Riemann tensor. So what is the transformation rule from there to there in terms of our omegas. Okay, so this question is the next question we're going to answer. It's going to be quite a long video because I'm going to go through the entire derivation, and then from there we're going to take a look at the Weyl tensor. The Weyl tensor has something to do with the difference between this guy and this guy. So with that being said, I hope you guys like this video, and please hit that like and subscribe button. Go onto my Patreon page if you want to support the channel, and I'll see you guys in the next one. Bye.